name is Ryan Tisthammer. I'm a freshman in the College of Science and Engineering at the University of Minnesota Twin Cities. I'm currently enrolled in Electrical Engineering 1301 in Introduction to Computing, taught by adjunct Professor Colleen. Over the past semester, we have done several Arduino projects to test our knowledge of hardware, software, and the connection between the two. For this video, I've recreated one of those projects where I turned my Arduino into a source measurement unit, and I hope to demonstrate that to you. Enjoy! So before we get started, you should know that I did not build this entirely from scratch. I was originally provided with blueprints, instructions, and a code that showed me how to link up the LCD display to the Arduino, and then how to get the LCD display to display whatever was put into the serial monitor. I took all that and then I modified this to create a source measurement unit. With that in mind, let's get started. This is what I was provided with. Now when I say that, I don't mean that the Arduino came attached to the serial monitor. I did that myself. However, I was provided with this diagram that shows me how to put those together, and then I was also given this code that tells the Arduino to display on the LCD display what is printed into the serial monitor. So before I go any farther, I'd like to explain why you can see my name on this sticky note and on these documents. That is because my professor told me to include my face in every frame so that you know that this work is my own. To spare myself this sanity of trying to cram my face into every frame and talk about this, and to spare your eyes from seeing this ugly mug all the time, I've instead chosen to include my name. I hope that when you see my name and hear my voice, you can believe me when I say that it is really me and not one of the other two Ryan Tisthammers on the planet. Unfortunately, because I chose to do this, I do have to make a disclaimer. Please know that when I attach my name to this code and this image, these were both taken from Simon Monk's book, 30 Arduino Projects for the Evil Genius. I am not claiming these works as my own. With that in mind, let's go on. Here we have the physical part of the project as it was provided to me. This diagram shows which pins on the Arduino correspond to which pins on the LCD display. I'm not sure why Arduino pins 2, 3, 4, and 5 correspond to LCD pins 7, 6, 5, and 4 respectively, when one could go the other way for simplicity's sake. But only some pins on the Arduino are PWM, so I didn't feel inclined to mess with the pin assignments. I'll spare you the show of putting the whole thing together. This is what the diagram looks like in real life. Now, because there are real words on this LCD display, I must have done it right. Next, we have the code that makes it happen. First, we have to include the liquid crystal library, or the Arduino would have no idea what these LCD commands are. Next, we associate the LCD pins to the Arduino pins as we have attached them. And this is another reason why I did not change the pin assignments, because then I'd have to work this out in the code, and that could be problematic. For the rest of the setup, we have serial begin, which lets us use the serial monitor, and LCD begin, which allows us to put things on the LCD display. It also prints Evil Genius rules, which is cute, but I didn't keep it when I cannibalized this code for my project. The rest of the loop just lets me print on the LCD display by writing into the serial monitor. So look, if I put in the pound sign, it should clear because it says if pound sign LCD clear. Done. So now I want to enter Ryan, a slash to move to the next row, and then Tisthammer. So this project was really cute, but I have much bigger plans. Let's talk about building a source measurement unit. This is the code I created for my source measurement unit. The only thing I took from the previous code is these 7 lines where I set up the serial monitor and the LCD display. Everything else is original, so when I put my name on this sheet of paper, it's more like an autograph than anything else, and I won't apologize to anybody. In the main loop, first I set the pins and initialize both the set voltage and the voltage to be read from the circuit, which is actually the voltage across a resistor in the voltage divider. The set voltage is set to the last value that's put into the serial monitor. That's what the serial, or VSET equals serial parse float does. If the value that it reads is a 5, then it initiates the called function scan, which I will discuss later. Otherwise, for any value between 0 and 4.99, it sends the voltage out to the circuit. The command analog write accomplishes that, but it only works on a scale of 0 to 255. So to change the value that's put into the serial monitor into a number that analog write will understand and execute properly, I need to multiply VSET by 255 and then divide it by 5. Next, the Arduino reads the voltage, as I mentioned before, across a resistor in the voltage divider of the circuit. And analog read only works on a scale of 0 to 1023. So to get that, or to get it from the value that is read by analog read into something that we can understand in terms of volts, I need to multiply the received value by 5 and then divide by 1023. After that, it displays the output of the Arduino in terms of volts, and then it also writes the measured voltage in terms of volts. Finally, as I mentioned before, we have this called function scan. It works a lot. It's a lot of the same code that I mentioned previously. In fact, I simply copy-pasted the main loop from the code, and the only thing I added was a for loop. This function will run whenever a 5 is entered into the serial monitor, and it orders the Arduino to increase the set voltage from 0 to 5 by increments of 0.2. For every one of those voltages, it'll do the same thing in the code where it sends out that voltage, and then it reads the voltage across a resistor in the voltage divider. And then again, it does the same thing where it displays the Arduino's output in terms of volts, and it shows the measured voltage across a resistor, again in terms of volts. This is the physical side of my source measurement unit. As you can see, everything from the provided project was included. I only added this circuit, which includes the resistor whose voltage will be read by the Arduino, this one. The circuit is a combination of a low-pass filter, which is this resistor and this capacitor, and a voltage divider, which are these two resistors. The low-pass filter is necessary to get a solid value for the voltage because the Arduino puts the voltage out using PWM, or pulse width modulation. This circuit may be difficult to see with this camera, so here's a diagram. Just a moment, there we go. The column on the left is a low-pass filter, which uses a grounded capacitor to filter out a lot of the modulation in the voltage. The only problem with using this low-pass filter is that I have introduced this extra resistor to the circuit, which may dissipate some of the power going to the voltage divider. However, because this resistor has a resistance of 1 kiloohm, and the resistors in this divider are on the order of 1 megaohm each, the effect will be minuscule. In the divider, we have two resistors. R2 is the resistor with a resistance of 1 megaohm, whose voltage will be read, because as you can see, a wire leads out of the circuit to the Arduino. R3 is originally another megaohm resistor, but its value can be easily varied by adding another megaohm resistor either in parallel or in series, which will effectively have the value of R3 or double it, respectively. I will be doing this in the demo to demonstrate that the SMU works for several different, albeit similar, circuits. To begin this demonstration, let's have both resistors in the divider have resistances of 1 megaohm. Using this formula for the output voltage of a voltage divider, the voltage measured by the Arduino should be 1/2 of the voltage put into the circuit, because it's 1 over 1 plus 1, or 1 over 2. Remember, however, that because I introduced this kiloohm resistor to the circuit, a very small amount of power in the circuit will be dissipated. So for values like 2 volts, the Arduino may measure 0.98 or 0.99 volts across the resistor. First, I will enter 1 into the serial monitor. The Arduino puts out 1 volt and measures 0.48 volts across the resistor. Next, for 2, it measures 1.0. For 3, it measures 1.48, and for 4, it measures 1.97. which is very close to 2 volts. I'll zoom in to show you how the scan function works when I put 5 into the serial monitor. As you can see, it started at 0. It's going up by increments of 0.2. And you can note for each value that it is approximately equal to 1/2, but it is just a little lower because of that kilo ohm. And it will go on until it hits 5, at which point it will be ready for a new value to be put into the serial monitor. Great. Now, as I hope you can see, I've added a second mega ohm resistor in parallel to this resistor. That makes the effective resistance of this small system to be equal to 1/2 of a mega ohm. If we consult this equation again, we can see that the output voltage should be equal to 1/2 over 1 plus 1/2 times the input voltage, which is equal to 1/3 of the input. I'll run the scan function to test that theory. As you can see, most of these values are approximately equal to 1/3, but it is just a little lower because of that pesky kilo ohm resistor. That kilo ohm resistor's effect is obnoxious, but including the resistor was necessary. For any smaller value of resistance, the low-pass filter didn't work and the LCD display would show gibberish because the Arduino has trouble understanding what kind of voltage it's reading. If you'd like to recreate this project, you have to use a kilo ohm resistor as well. Finally, I've moved this mega ohm resistor so it's now in series with the second mega ohm resistor of the voltage divider. That makes the effective resistance of these two together to be 2 mega ohms. If we bring back this equation one more time, we can see that the measured voltage should be equal to 2 over 1 plus 2, or 2/3 of the input voltage. I'll run the scan function one more time to test that theory. It's a little difficult to keep up with the SMU and do the math in my head, but we can see for 1, it measured 0.65 volts, which is roughly 2/3 of 1. This SMU works well for 3 different circuits, so I would definitely call it a success. In review of the course EE1301, I came into the course thinking it would be a bit of a drag because I'd never been interested in programming. I'd built a computer before I even came to the U, but nothing ever went wrong with it, so I never needed to fix it. I was blissfully ignorant of the real applications of hardware and software and how they could have helped that process. And then as an electrical engineering student, I only joined because I wanted to work with Tesla coils and lasers. I wanted to play with them and, you know, find their applications. So there was never really any call for me to learn about programming or computing in general. But now I've seen the applications, both practical and fun, of hardware, software, and, you know, putting them together. I've shown you the practical applications I've learned where I built a SMU out of an Arduino, and then for fun applications I was part of a group in the class where we built a laser harp, and yeah, that was definitely very fun. So clearly this class has taught me a lot about, you know, what it was supposed to, so computing, programming, hardware, software, etc. So I guess in conclusion, I don't really see what I've learned as pertinent to my future career, but I'm very glad that I took the course because who knows, maybe I will eventually end up as a computer engineer or something similar, and it's also just very comforting to know that if there's ever a problem with my computer, I can troubleshoot it. If I ever need to build something with my Arduino to serve some very small purpose around the house, I can do that. So with that in mind, I'm very glad that I took the course, and I definitely recommend it for future electrical engineering students.